Okay, yesterday we have seen problems in 4th unit and also 5th unit. So we have completed problems on comparison test. 2 problems, example problems we have completed. Okay, today we'll see the D'Albert's ratio test and also ratio test. First, we have the ratio test. Okay, so ratio test, we have the definition is that let summation an and summation bn be two positive terms be two infinite series of positive terms and let an plus 1 by an is less than or equals to bn plus 1 by bn for all n greater than or equals to n. For a given n, then if summation bn converges, then summation an converges. Okay, this is the definition of the ratio test. The condition is that we have to find an will be given in the question. We have to choose bn and we have to find an plus 1 and also bn plus 1. And if an plus 1 by an value is less than or equals to bn plus 1 by bn, then if summation bn, we will be choosing bn value, if it converges, then an also converges. Okay. So next one is D'Albert's ratio test. This is very important. On this we have problems. Ratio test. So for this, the definition is that let summation n equals to 1 to infinity an be a series with positive terms such that limit n tends to infinity an plus 1 by an if this is equals to L, okay, small l, then first condition is that summation an converges if L is less than 1, okay. Second one summation an diverges if L is greater than 1, okay. Third condition is if L equals to 1, then test fails. Okay. So D'Alembert's ratio test, we have the condition is that let summation A n be a series with positive terms such that when you find the limit of A n plus 1 by A n, if you will get the value as some L, okay, then that L will be converges, means whatever the value will be there, that L you may get in the problem X or L, anything, okay. So if that X or L value is less than 1, then summation A n converges. And if X is greater than 1, then summation A n diverges. And if you take L equals to 1, then test fails. Okay, on this we'll see the example problem. So how to solve the given problem with the help of the D'Albert's ratio test. Okay. So this is the exercise problem you have. So the problem is summation n equals to 1 to infinity n plus 1 by n cube into x to the power of n. Okay. N plus 1 by n cube, n plus 1 by n cube into x to the power of n. Okay, this is the problem you have to solve with the help of D'Alembert's ratio test. So for this, the given an is here an is equals to n plus 1 by n cube into x to the power of n. Okay, we need n plus 1, that is in place of n we have to substitute n plus 1. So here if you substitute, you get n plus 1 by n plus 1 whole cube, okay, into x to the power of n plus 1. Now we substitute an and an plus 1 values in this limit. That is limit n tends to infinity. First an plus 1, now this is n plus 2 by n plus 1 whole cube into x to the power of n plus 1 into, that is divided by an we have, or else you write like this. An by an is equals to limit n tends to infinity. So n plus 2 by n plus 1 whole cube into x to the power of n plus 1. Okay. Divided by an means whatever the in denominator will be there, that comes to numerator, and numerator will come to the denominator. So this is into n cube by into in denominator x to the power of n. Okay. So okay, this value is equals to, that is limit n tends to infinity n plus 2 by, or else here you take n value outside. So 1 plus 1 by 1 plus 2 by n. And if in the denominator you take n value, that is n cube will come outside, and it will be 1 by 1 plus 1 by n whole cube. Here you can split this one, here n cube is there. So n cube into n means you will get it as n to the power of 4, and x to the power of n into x we can write. Okay. So here n plus 1 is there. So if you take n common, 1 plus 1 by n into x to the power of n. So this x to the power of n, this x to the power of n will get cancelled. And here n cube into n means n to the power of 4. So this also will get cancelled. So limit n tends to infinity, 1 plus 2 by n by 1 plus 1 by n whole cube into 1 plus 1 by n. Okay, this we have. Here in the numerator we have x. Okay, now substitute n value as infinity. So when you substitute n value as infinity, we will get 1 plus 2 by infinity by 1 plus 1 by infinity whole cube 1 plus 1 by infinity. Okay, so into x. So 1 plus this is 0. So in the numerator 1, here 1 plus 0, 1 plus 0. So 1 by 1, this is equals to x. So we got the value as it is equals to x. Now from the definition of the D'Albert's ratio test, we have that whenever an plus 1 by an is equals to L, we have the three conditions now. So with the help of that conditions, we have to find whether it is a convergent or divergent. Okay. So if x is less than 1, x is less than 1, summation an is convergent. If x is greater than 1, summation an is divergent. Okay. Next, third one is if x equals to 1, x equals to 1, the test fails. So these are the three conditions. If x is less than 1, it is convergent. If it is greater than 1, it is divergent. And if it is x equals to 1, the test fails. Now for solving the problem, we have to substitute x value equals to 1 in the given an. Then we have to find the limit of that one. From that, we can find whether it is a convergent or divergent. If x equals to 1, then an is equals to, so then an is equals to what is given in the question? N plus 1 by n cube. Okay. So this is the an value. Now from by the comparison test, we have to choose bn value. Choose bn. So yesterday we have seen bn value will be chosen highest power of n in the numerator and the highest power of n in the denominator. So highest power of n in the numerator is n and in the denominator is n cube. So if you cancel out this, you'll get 1 by n square. Okay. So 1 by n square. So this is from the p test. We know that p value is 2, which is greater than 1. So it is convergent. By p test, p value equals to 2, which is greater than 1. Therefore, summation bn is convergent. Okay. Now we'll substitute the an and bn values in the formula. That is limit n tends to infinity. An by bn is equals to limit n tends to infinity. What is an? An is n plus 1 by n cube. And bn value is 1 by n square. That is n square by 1 will get. So it is equals to limit n tends to infinity. If you take Here n value outside n into 1 plus 1 by n into n square by n cube we have. So n cube and n cube will get cancelled. And if you substitute the n value as infinity, 1 plus 1 by n will get as 1. That is 1 plus 1 by infinity is 0. So 1 plus 0 is equals to 1. So we have got a finite non-zero number we have got. So therefore, whatever the an value is there, that is convergent. Okay. So thus, but summation bn is convergent. So before that you write thus summation an and summation bn act alike. Okay. But summation bn is convergent. Hence, summation an is convergent by comparison test. Okay. So like this, you have to solve the problem for the D'Alembert's ratio test. So by comparison test. Okay. So this is the, in exercise you have problem, that is MEQ question will be there, no? There it is there. You can see some more example problems in your textbook and practice them. Okay. Next we have the Cauchy's root test is there. So Cauchy's root test, we have definition, and with the help of the definition you can solve the problem. If in the power you have n will be there in the power, then you can use the Cauchy's root test. So in Cauchy's root test, an to the power of 1 by n will be there. Okay. With the help of that, n and in the power whatever n will be there, both will get cancelled and it will be converted into simple form such that we can solve the problem. Okay. Next is the Cauchy's root test. So Cauchy's root test definition is, let summation an be an infinite series of positive terms if there is an integer n, integer capital N, and positive number lambda less than n, such that an to the power of 1 by n is less than or equals to lambda for all n greater than or equals to n, then summation an converges. Okay. And if there is an n, there is an capital N such that an to the power of 1 by n is greater than or equals to 1. Okay. For all n greater than or equals to n, then summation an diverges. Okay. So this is the definition of the Cauchy's root test. That is, let summation an be an infinite series of positive terms. If there is an integer, we are taking that as a capital N, and positive number. Here one number, we are taking it as lambda, which is less than 1, such that an to the power of 1 by n. Whatever this value is there, this value, if it is less than or equals to lambda, where lambda is less than 1. Okay. So if this value is less than 1, then summation an converges. If this value is greater than or equals to 1, then summation an diverges. So the main thing is these 2 points. If this value is less than lambda or less than 1, if the converges, if this value is greater than or equals to 1, then it diverges. Okay. We'll see one example problem. That is summation n equals to 1 to infinity n root n minus 1 by 100 to the power of n. Okay. So in the question already I have told, it will be not mentioned whether to solve this by any test. So by seeing the problem, you have to understand and you have to apply any test to solve the problem. So here easily for Cauchy's root test, you can identify that one. In the whatever the an value will be there the power will be n. So whenever in the power n will be there, so you can use the Cauchy's root test. Why? Because an value to the power of 1 by n we are doing. So whenever you will do that, n will be getting cancelled and this will be the an value. Okay. So let here an is equals to, let an is equals to n root n minus 1 by 100 to the power of n. Okay. So then an greater than 0. So just you write here sentences, whatever it is there. Then an greater than 0 for all n greater than or equals to 1. An to the power of 1 by n is equals to n root n minus 1 by 100 to the power of n whole to the power of 1 by n. Okay. This n and n will get cancelled. So what is remaining? So only n root n minus 100 will be there. So it is equals to n root n minus 1 by 100. Okay. So here we know that n tends to infinity. So n is greater than 0. So if you take n value as equals to, greater than or equals to 1 is there. So if you take n value as 1, what will happen? 1 root 1 means the value is 1. So 1 minus 1 by 100. If you substitute, what you will get? It will be 99 by 100, which is equals to 0.99. Means this value is less than lambda. So whatever the summation an is there, it is convergent. So n minus n root, this tends to 1 minus 1 by 100. So here we are substituting n value as 1 as n tends to infinity. Okay. This means that there exists n such that there exists a capital N such that an to the power of 1 by n is equals to n root n minus 1 by 100, which is less than, here less than is there, or else I will write here if you will get any confusion, such that an to the power of 1 by n is equals to n root n minus 1 by 100, which is less than 1 minus 100. 1 minus 1 by 100. Okay. So you can take here this value will be 99 by 100. Okay. 100 minus 1 is 99. 99 by 100. This value is equals to, okay, whatever this value will be there, this value will be less than 1. Okay. So this value is less than 1. So for every n greater than or equals to capital N, now by Cauchy's root test, Cauchy's root test summation n equals to 1 to infinity, an is convergent. So like this, you have to solve the problem with the help of the Cauchy's root test. So first thing is, in the power n is there means you have to use this test. So first cancel out the n, then whatever the value is there, that value you see whether it is less than or equals to 1 or greater than or equals to 1. Okay. So on Cauchy's ratio test, we have one more example problem is there. So that is the exercise problem. Second one is summation n equals to 1 to infinity n to the power of q by p to the power of n. Okay, this is the question. N to the power of q by p to the power of n. Okay. So here direct like this simple, only n terms are not there. Here q is there and also here p is there. And here base we have n and here power we have n. Okay. For this, two cases will arise. One case is that p is greater than 1 and another case is p is less than 1. Okay. For two cases, we'll see what you'll get, whether it is a convergent or divergent. Okay. We need to consider two cases. Two cases, that is p is greater than 1 and p is less than 1. Okay. First of all, n q to the power of 1 by n. Okay, this value is equals to, that is n into, if you take inside power to the power of q. Okay, just you are interchanging here. So as n tends to infinity, that is infinity to the power of 1 by infinity means you will get infinity to the power of 0. So which value is 1? 1 to the power of q means its value is 1. Okay. So this value tends to 1 as n tends to infinity. So whenever n is tending to infinity, this value is 1 here. So we know from the formula, that is limit n tends to infinity. So whatever the given problem is there, that is a to the power of 1 by n. Cauchy's root test means n to the power of q by pn to the power of 1 by n is equals to limit n tends to infinity. So n to the power of 1 by n to the power of q by p to the power of n into 1 by n. So these two will get cancelled and this value is 1. So you will get it as limit n tends to infinity 1 by p. Okay. So we are getting the value as 1 by p. So we got P no. So when P is greater than 1, what will happen? And when P is less than 1, what will happen? We have to see that one. So first case is if P is greater than 1, if P is greater than 1, then 1 by P will be less than 1. Okay. 1 by P will be less than 1, and hence there exists capital N such that NQ by P to the power of N whole to the power of 1 by N value will be less than 1. Okay, whenever it is less than 1 means with the help of Cauchy's root test, it is convergent. Okay, then by Cauchy's root test, summation AN is convergent. Summation AN is convergent. Okay, second case is, this is the first case, and second case, if P is less than 1. Okay, so if P is less than 1, then 1 by P is greater than 1. Okay, and hence there exists here we take it as capital M such that n to the power of q by p to the power of n whole to the power of 1 by n is greater than 1. Okay, whatever the value you will get, that will be greater than 1 for all n greater than or equals to capital M. Then summation by Cauchy's root test summation an is divergent. Okay, so like this you have to solve the problem. So in the power, if you see n, you can fix that, you can use the Cauchy's root test. So take out that n whatever there in the power and then simplify that one and solve the problem. So by this we are completing the fifth unit. So in fifth unit, the important theorems are, so exercise problems are there. So comparison test, uh, statement and also proof will be given for the 10 marks question. Next, page number 66, we have Cauchy's root test is there. 67, page number 5.1.14. This is a very important one. It is the Cauchy's condensation test is there. So on this problems, only one or two problems are there, but the statement and proof is very important. So this is the 10 marks question. That is 10B question will be from this one. Cauchy's condensation test. Okay. So some exercise problems in page number 68. I have told the problems. So you practice 69 page number worked out exercise problems. Next we are going to the sixth unit. By completing the sixth unit, we will complete the block 2. So in sixth unit, we have the concept of alternating series. So in the name itself, it is there that it is alternating. Alternating means one positive sign and one negative sign will be there in the given terms. Okay. Whatever the series is there in that series, combination of positive and negative terms will be there. So that's why it is called as alternating series. So it is unit 6. Alternating series. Okay. So the definition of alternating series, you can see in the textbook, it is there. So it is given as an infinite series formed by positive and negative terms occurring alternatively is called an alternating series. This is one of the definition. But in your textbook, it is given that a sequence xn of non-zero real numbers is alternatively if the terms minus 1 to the power of n xn are all positive or all are negative. Okay, a sequence x to the power of n of non-negative, non-zero of non-zero real numbers, non-zero real numbers is alternating if the terms will be in the form of minus 1 to the power of n xn are all positive or all negative near numbers. Okay. So that is, it is a combination of positive and negative terms. It is called as alternating series. And one more definition we have in this, it is the conditionally convergent. So when a series is called as a conditionally convergent, that we can see it is a, if summation an is a convergent series and summation, that is modulus of an, is divergent, we say that summation an is conditionally convergent. That means summation an is a convergent series, and whereas if you find the modulus of that an, if it is a divergent series, then we say that summation an is conditionally convergent. So on this also you will have the theorem, that is the conditionally convergent. Conditionally convergent. So if summation an is convergent and summation bn is divergent, then summation an is conditionally convergent. Okay. So even in this 6th unit, we have the Leibniz test is there. This Leibniz test is very important. Okay, Leibniz test will be asked for 10 marks question. That is 10B question will be this question only. So state and prove the Leibniz test will be there. Just I am telling what is the statement of the Leibniz test. Okay. So Leibniz test, if in an alternating series summation an, the equation that is a an is the given sequence in the given question. Okay. If the sequence modulus of an is a decreasing sequence. Okay. When you find the modulus of the given an, If it is a decreasing sequence converging to 0. As we know, whenever it is a decreasing sequence, it will be compulsory converges to 0. If it satisfies this condition, then the series is called as a convergent series. Okay. So this is the statement of Leibniz test. If in an alternating series, summation n equals to 1 to infinity an, the sequence that is modulus of an is a decreasing sequence converging to 0. Then series summation n equals to 1 to infinity an is convergent. Okay. This proof you have in your textbook, so you can practice that proof. And also on this, you will have the problems. So by seeing the problem, you can identify in the numerator compulsory -1 to the power of n or n minus 1 will be there. So that means one you will get as a positive term, another term will be the negative one. Okay. So by seeing that, we can identify that the problem can be solved with the help of Leibniz test. So one example problem is, okay, summation n equals to 1 to infinity minus 1 to the power of n minus 1 by 2n. Okay. So solution is, let the given series be or you can take here an is equals to minus 1 to the power of n minus 1 by 2n. Okay. Now sequence of modulus of an is equals to, I'm writing above, that is sequence of mod an n equals to 1 to infinity is equals to, so that means whenever we take mod means this minus 1 symbol it will go. So only 1 by n, that is 1 by 2n will get as the sequence n equals to 1 to infinity. Okay. 1 by 2n in the sense it will take n value as 1 by 2. Next it will take the n value as 2, 1 by 4. Next, like this, whatever the values you are getting, they will be converging. It is a decreasing sequence. The values are going on decreasing, and also it will converge to 0. Therefore, this is a, by Leibniz test, it is convergent. It is a decreasing sequence. So it is equals to summation 1 by, that is 2n, n equals to 1 to infinity, is a decreasing sequence and converges to 0. Okay. So by Leibniz test, the series is, the given series is convergent. So like this, we have to find the problem with the help of Leibniz test. So next we have one more problem we have. So these are the exercise problems we have. That is MEQ questions will be there, no? So there we have, that is summation minus 1 to the power of n by log n. Okay, this is the given one. So solution is that here let an is equals to minus 1 to the power of n by log n. Okay, if you take the modulus of this one, you will get 1 by log n. Okay, so then that whatever the values will be there, that will be decreasing sequence, and also it will be converges to 0. So the by that process we can do, or with the help of, that is, so that an plus 1 value is equals to minus 1 to the power of n plus 1 by log n plus 1. Okay. So now log n plus 1 1 by log n plus 1 is less than 1 by log n. Okay, if you will find the modulus of this one, so modulus of an and also modulus of an plus 1, we will get 1 by log n and also 1 by log n plus 1. So from that we can tell that 1 by log n plus 1 value is less than 1 by log n, because n plus 1 is greater than n. Okay, so implies log n plus 1 is greater than log n. Thus, we have an plus 1 is less than an for every n. Okay, and sequence an is monotonically decreasing sequence, and sequence an converges to 0. Okay, because how it is converging and how you are getting the value as 0 means, because limit n tends to infinity, 1 by log n is equals to 0. Okay, so when you take out this negative sign, 1 by log n you get. So when we substitute the n value as infinity, so 1 by infinity you will get, it is equals to 0. So by this we are getting this value as equals to 0. Hence by Leibniz test, given series is convergent. Is convergent. Okay, you can write here modulus of an is equals to 1 by log n. And here modulus of an plus 1 is equals to 1 by log n plus 1. Okay, so these whatever the values are there, those values are 1 by log n plus 1 is less than 1 by log n. Okay, so this is one of the exercise problem. One more problem is there in the exercise. So how you can solve this problem? So different, not only direct, that is minus 1 to the power of n, whatever it is there, that you should take out, and if you can find the, with the help of limit n tends to infinity, 1 by log n value is a, it is a decreasing sequence, and with the help of this you can tell that it converges to 0. Okay, so directly like that also, or else you can use this method for solving the problem. Next, one more problem we have. That is summation n by n plus 2. Okay. Here we don't know with the help of what we can solve this problem. Okay. So here to the power of n is not there. So minus 1 is not there. To say that with the help of Leibniz test we can solve this problem. Okay. So for this here the given an is here an is equals to n by n plus 2. Now an plus 1 is equals to n plus 1 by n plus 1 plus 2. It is equals to n plus 1 by n plus 3. Okay. Now an minus an plus 1 is equals to an value is n by minus n plus 1 by n plus 3. So if you take the denominator n plus 2 into n plus 3, and if you cross multiply this one, that is n plus 2 into n plus 3, no? So n plus 2 means n plus 3 into n minus n plus 1 into n plus 2. So if you simplify this, so it is equals to n square plus 3n minus, okay, this is n square, n into n square plus 2n plus 1 means 3n plus 2 by n into n square, 3n plus 2n means 5n plus 3 to the 6. Okay. So it is n square plus 3n minus n square minus 3n minus 2 by n square plus 5n plus 6. So n square and 3n will be gets cancelled. So it is equals to minus 2 by n square plus 5n plus 6. Okay. This value we got as a negative value. So whenever we will get the negative value means this value is 0. That is less than 0. Okay. So thus an value is less than an plus 1. Okay. So we have seen that is what is the definition of a monotonic decreasing function and monotonic increasing function. So whenever an value is less than an plus 1, then it will be a monotonic increasing function. Okay. And sequence an is monotonically increasing function, and so this is a for Leibniz test we need it is a decreasing function. So this is the increasing function, that is increasing sequence, and also limit n tends to infinity an is equals to limit n tends to infinity n by n plus 2. So it is equals to limit n tends to infinity n by, in the denominator if you take n common, 1 plus 2 by n. Okay, so you are able to see or not. So it is equals to limit n tends to infinity n by, if you take n common, 1 plus 2 by n. Okay. So n if you gets cancelled, it is equals to limit n tends to infinity 1 by 1 plus 2 by n. So when you substitute n value as infinity, you will get as 1 by 1 plus 0. That means it is equals to 1. Okay. So you are not getting the limit value as 0. So and even it is a monotonically increasing sequence. Therefore, thus the given series is, thus the given series is not convergent. So the given series is not convergent. So like this, you have to solve the problem with the help of the Leibniz test. We have to see the conditions of the Leibniz test and you have to solve the problem. So in Leibniz test, in page number 75, 6.2.6 we have. So it is the Dirichlet test. So for this one, suppose that each an of a given series can be expressed as a product bn cn, where bn is a decreasing sequence of positive terms with limit 0 and the partial sum sequence of the series summation cn is bounded, then summation an is convergent. Okay. So here in this test, whatever the an summation an will be there, that you can write it as in the product of bn and cn, where Bn is a decreasing sequence which is converging to 0. Okay. And Cn, whatever Cn is there, Cn is a bounded sequence. So here we have two conditions. One is Bn is decreasing sequence which is converging to 0 and Cn is a bounded sequence. So then if these two conditions are satisfied, then summation An is a convergent. Okay. So the proof you have, this is also 10 marks question, that is 10 B question. You will get either this test or Leibniz test. Okay. So 6.2.7 you have the Leibniz test is there. Statement and proof you have. So for this proof, whatever Leibniz test, proof and remark you have to combine and you have to write the proof for this one. Okay. Next, page number 79. Rearrangement of terms is there. So this is also 6.3.2 theorem, whatever the theorem is there, and 6.3.3. These two theorems also will be asked in some cases. These two theorems will be asked for the 10 marks question. So whatever the problems are there in 81 page number, just now I have told those problems. And 82 page number, if you see the MEQ questions. So first question and second question, these two are the regularly asked question with the combination of problem. So you have problem no? By Leibniz test and also Dirichlet test, you have two problems are there. These two problems will be asked. So next week on Saturday 8th we have class. So there we will start the block 3. It is the Riemann integrability is there. So in Riemann integrability, we'll see what is the definition of the, means what are the conditions for a function to become whether it is a Riemann integrable or not. So the conditions are there. If you know those conditions, so we can see whether the given function is Riemann integrable or not. Third block is whole about the Riemann integrability. And the fourth block is about the mean value theorems are there. That is a uniform convergence. On that you have problems are there. Mean value theorem on integral calculus. That is fourth block is about pointwise convergence and uniform convergence, infinite series of functions, and 12th unit is power series. So in 12th unit you have some problems are there which you will get as the 8th question, that is 5 marks question, 8th question you will get. There we have to find radius of convergence and interval of convergence. Okay. So next week we'll see the third block